Hi everyone, we're going to talk about straight line motion today, and so I've set this diagram up here along an x-axis. The reference point here is marked by the red cross, so typically the reference point would be at 0 on the axis. The initial position of our blue dot here is not 0. Typically, commonly x0 will equal 0, but just to be general, I'll say that it could start anywhere, and we have a constant acceleration in this discussion. Constant acceleration, so that's important. Now, how do we start? Well, we start from constant acceleration. Now, we know, of course, that velocity is the integral of a dt. Well, one other thing I should mention, because it's straight line, we won't be worrying about I and j components for vectors. So velocity is a vector, acceleration is a vector, and we'll simply indicate direction by using positive values for moving to the right and negative values moving to the left, just as we would on an x-axis. So one-dimensional motion is a little bit easier because we don't have to worry about I and j components. Now, how will this look? Well, the integral of a dt is at plus a constant, and this will be our velocity. Now, what's the constant evaluate to? Well, we can see here the initial velocity is sometimes called v naught, sometimes called u. So I'll let t equal 0. In other words, my initial velocity applies. A times t would be 0. And so the constant of integration is the initial velocity. This gives then our formula v equals v naught plus a times t, also sometimes written as u plus a times t. The symbols here for initial velocity are interchangeable. It depends a little bit on which textbook you've read. So we therefore would have a nice formula. We could just summarise then. Let's go v equals u plus a times t. There's our first equation of motion. That's lovely. Now, how will we find displacement? X as x position equals the integral of v dt. Well, we know that v is u plus a times t dt. Integrating will give ut. A is constant. T becomes t squared. Divide by the new power plus a constant of integration. Now, how do we evaluate? Again, we consider the initial conditions. We let t equals 0. Now, as noted earlier, when t equals 0, the original position of our particle was designated as x naught. So we have x naught. U times t would be nothing. A times t squared over 2 would be nothing. Again, the constant of integration is the initial position, x naught. So we have the formula x equals ut, commonly written as 1/2 at squared plus x naught. Now that's the most general form of the equation. As I said, often x naught equals 0. In other words, often we choose that the beginning point for the particle's motion is the origin of the coordinate system. And if that's the case, then we get that x equals ut plus 1/2 at squared. That's the familiar equation that you might have seen in physics. And that's our second equation of motion. X here represents the position along the x-axis, and in the case that x naught equals 0, it would also represent the displacement. If x naught didn't equal 0, which is sort of the previous step back, this would be x minus x naught, or you could leave the x naught there either way. But just remember, commonly x naught equals 0. Now, if we were to take if we were to take our first equation, we could rewrite that as v take u divided by t. That's from equation number 1, just by rearrangement. Subtract u, divide by t. And sometimes this is the definition of acceleration. We could think of that as the definition of acceleration. And now if I substitute this into equation 2, I'll be left with x equals u times t plus, now I have 1/2. Instead of acceleration, I'll put v take u over t, and then I'll still have t squared. Well, that t cancels with the squared. I could have u plus v take u over 2. I could factor out the t. Now, using a common denominator, that should be 2u over 2 plus v take u over 2. Now I think you can see that 2u take u is just u, and we still have plus v, we still have multiplied by t. So that's a third equation of motion, a different way of finding position, or x. Some people will write this in the form of x equals the average velocity multiplied by time, and the average velocity then is the initial plus the final divided by 2. So that's not really an equation of motion, but the third one is. That's quite handy sometimes to use. So we've got, just as a recap now, we've got v, we've got a formula for x for the position, we've got an alternative formula for the position that doesn't need us to know the acceleration. That's handy. Now, the last thing I want to do is still this final equation, x u plus v over 2 times t, but I want to come at t from another direction. Do we note back here in equation number 1, equally we could rearrange this as v take u over a. That gives us an expression for time. V take u over a, just multiply by t, divide by a. Now down to here, we'll get rid of that. That's really not used very common. So what we'll do is now we will sub for time in equation 3. So it starts with x, u plus v over 2. Now instead of time, we had back here v take u over a. V take u over a. Let's multiply both sides by 2 and a, so I would have 2 times a times x, and that's v plus u, v minus u. That looks like the difference of 2 squares to me, so this should be v squared take u squared, and often this will be written as v squared equals u squared plus 2 times a times x. And that's the fourth common way of writing the equations of motion. And remember, all of these apply for constant acceleration only. That's enough for now. In the next video, we'll have a quick example of how to use these.